Certain crystals and solutions possess a natural ability to rotate the plane of polarization about the direction of propagation. The ability of a crystal or a solution to rotate the plane of polarization of plane polarized light by a certain angle is called optical activity. And substances which have the ability to rotate the plane of polarized light passing through them are called optically active substances. Quartz and cinnabar are examples of optically active crystals, while aqueous solutions of sugar, tartaric acid, are optically active solutions. In this video content, we shall learn how to measure the optical activity of sugar solution by an instrument known as Laurent's half-shade polarimeter. A polarimeter is an instrument that is used to determine the optical rotation of solutions. This figure shows the instrumentation of Laurent's half-shade polarimeter. Unpolarized light from a source is allowed to fall onto a nickel prism designated as N1, which creates linearly polarized waves. The plane polarized light is then sent to a special device known as half-shade plate. Light from the half-shade plate then goes to a glass tube containing the solution whose optical activity is to be measured. In this case, we will take the sugar solution with a specific concentration inside this glass tube. While passing through the glass tube containing the sugar solution, the polarization angle of the light beam will be rotated by a specific amount theta. To analyze the light that is coming from the sugar solution, another nickel prism designated as N2 is used. So N2 is an analyzer which could be rotated about an axis and is having verniers V1 and V2 to take the measurements. The light intensity from the nickel prism N2 could be seen using a telescope. So this is the arrangement of the Laurent's half-shade polarimeter. We shall now discuss about the design of the half-shade plate. A half-shade plate is an arrangement that is made by cementing quartz and glass. So one half of the half-shade plate is made up of quartz and the other half is made up of glass. An important point with regard to the quartz plate is that its optic axis is parallel to the line AB, which is separating the quartz plate and glass. The quartz plate is a half-wave plate. That is, the quartz plate is having a thickness d, which will produce a path difference of lambda by 2 or a phase difference pi between the E and O rays. Let us assume that the polarization of the incident light is along OP. This vector makes an angle theta with respect to vertical. When incident light passes through glass, it passes as such. Now let us see what happens when light passes through the quartz half-wave plate. So this is the direction of the incident vibrations. When it enters the quartz half-wave plate, it splits into two, the ordinary wave and the extraordinary wave. Inside the quartz plate, the ordinary ray travels faster than the extraordinary ray, and while coming out of the quartz crystal, there is a phase difference of pi radian between the ordinary and extraordinary components. Because of the phase difference of pi radian between the ordinary and extraordinary rays, while coming out of the quartz crystal, they combine to result in a wave that is oriented along OQ. So this angle was theta and this angle is also theta. So that the total angle with which the vibration inside the quartz crystal is rotated is 2 theta. That means the half-wave plate turns the plane of polarization of the incident light through an angle 2 theta. In summary, light coming out of the glass plate will be having vibration along this direction, whereas the vibrations coming out of the quartz half-wave plate will be along this direction. Initially during the experiment, we'll remove the glass tube containing the sugar solution. When we rotate the nickel prism N2 along an axis like this, for different orientations of N2, one side of the half-shade plate will be brighter or darker. If the principal plane of the nickel N2 is aligned parallel to OP, the plane polarized light emerging from the glass plate of the half-shade plate appears bright. The quartz side is dark because the polarization of light from quartz is along OQ. If N2 is oriented along the direction OQ, then the quartz side will be brighter and the glass side will be dark. In case if N2 is oriented along the direction OA, then both the quartz side and glass side will appear equally bright. If the nickel prism N2 is oriented along the direction CD, then both sides of the half-shade plate will be darker. To find the specific rotation of a solution, the analyzer is first placed in the position of equal darkness without the solution in the tube. The reading on the circular scale is then noted. Next, the tube is filled with the optically active solution of non-concentration and placed between the half-shade plate and the nickel prism N2. The optically active solution in the glass tube changes the direction of polarization of the light beam. Now let us assume that the direction has been changed to OP prime. Let us assume that the corresponding angle is theta prime. In the quartz side, the polarization vibration rotate by an angle 2 theta prime, and now let us assume that the direction of polarization is along OQ prime. When we introduce the optically active solution between the half-shade plate and the nickel prism N2, the field of view will be partially illuminated. Now, we'll rotate the analyzer N2 till the field of view becomes equally dark. After making the field of view equally dark, the reading on the circular scale is noted again. The difference between the two scale readings gives the angle of rotation of the plane of polarization caused by the solution. The specific rotation of the liquid is given by the formula S T lambda equal to theta over L times C. Here theta is the rotation caused by the solution in degrees, L is the length of the tube in decimeters, and C is the concentration of the solution in gram per cc. So this equation can be written as N times theta over L, which is expressed in centimeter, and the concentration in gram per cc. By performing the experiment, we'll find out the specific rotation angle theta. We have the value of L and C, and substituting in this equation, we can find the specific rotation of the liquid. In the actual experiment, different concentrations of the solution are taken and the corresponding angles of rotation are determined. A graph is plotted between the concentration C and the angle of rotation theta. The graph will be a straight line. The slope of the curve gives delta theta or delta C, and using the previous equation, we can find the specific rotation of the optically active substance.